and I haven't even, I'm recording now, so okay, so go over some stuff with complex numbers. I have a little bit extra in here beyond what was on the homework, and you can stop me if you think it's something you don't need to know, or ask me more if you think you would like to know more about it. And for those of you who are tuning in for the first time, I do usually try to post these recordings, but I can't guarantee, and if you're ever here in person, you need to always double check if you want me to post the recording to make sure that I am in fact recording it, and looks like I am now. Also, for those of you who, if you can't come to the sessions, my name's Rebecca. I was the SI for Circuits 1. I didn't see a whole lot of you there until exam time, just because I had to have it in the morning, and it started late. But I'm the same person as from Circuits 1, and I do love answering questions. And I have an office in the ERAD building, and you're welcome to come by and send me an email and ask when is a good time to come by and ask questions. And at some point I'll post formal office hours, but really the best thing to do is just contact me and see if we can set something up. All right, well, let's talk about complex numbers. So what is a complex number?
QR code.
I do have a QR code. That's the other thing you always have to remind me of. So let's see if I have it.
Participant responsibilities.
Right, those are your responsibilities. Let's see. Teams has changed, and now I can't find anything anymore. This is not the right one. So yesterday was a successful session, and today will be a successful session. All right, yeah, so here's the QR code. I have even already dragged it into the right folder. I thought I had. I did. Okay. All right, so what is a complex number?
Oh, you asking me?
Sure. Or, yeah, okay. Only if you want to answer.
Has a real part and an imaginary part?
Yeah. Has a real part and an imaginary part. Either of which could be 0. So J is defined to be the square root of -1. And so if I have a complex number, J equals A, Z equals A plus JB, the real part of Z is A, and the imaginary part of Z is B. You'll notice that when we do the real part and the imaginary part, we don't have the J here in the imaginary part. These things are actually both real numbers, A and B. A and B are real. So it's kind of strange that the imaginary part is a real number, but it's the real number that's attached to J. Okay, so as a real part and imaginary part, either of which could be 0. So that means that, pi minus j2 is a complex number, but so is pi, with the imaginary part equal to 0, and so is negative j2. Those are all complex numbers. Pi minus j2 is complex. Pi is real. And minus j2 is imaginary. Okay, does a complex number represent a vector or a scalar in circuit analysis? Briefly justify.
We haven't gotten to that yet.
Okay, so it represents a vector, and the reason that we use it is it has a scalar magnitude and it has an angle, and we'll see how that works in a little bit. So it's scalar magnitude and an angle, and when we list it with the scalar magnitude and the angle, we call that a phasor. And so a phasor is something that is, pause the recording. All right, so when we have a phasor, we would list it, we would write it as something like 5 angle 30 degrees. And what that gets us is the 5 is the magnitude, and 30 degrees is the angle. And that's the same as saying 5e to the j 30 degrees. And I think y'all have seen them written like that. It's a shortcut way of doing that. Okay, why are complex numbers or phasors useful in AC steady state analysis? So, why all of a sudden, you might have learned about complex numbers in high school, and it's like square root of -1, when are we ever going to use that? And somebody might have said electrical engineering. If somebody was really on top of things, they would have said quantum mechanics. But the reason why it's useful in steady state analysis is because we have AC, we have alternating current, and so our current comes in the form of a sine wave, or sinusoidal. So our current and our voltage and everything is sinusoidal. And that is difficult to deal with if we had to carry around sines and cosines everywhere. But exponentially, e to the j theta equals cosine theta plus j sine theta. And exponentials are very easy to work with, especially compared to the trig functions. And so what we do in electricity and magnetism, and most people don't realize what we're doing, in electricity and magnetism, you really could do everything without complex numbers. It would be a pain. It would be a mess. It would be very difficult to do. And most people don't know that, so you'll hear people who'll tell you differently. But you could. Quantum mechanics, no. Quantum mechanics is so weird that you have to have imaginary numbers. But here, you could do it without, but using exponentials instead of using the trig functions makes everything a lot easier, and then we just really use the real part, The real part is what we actually see. So whenever you're talking about, when you get to talking about real power, that's going to be the real, what you actually see. And so when we write things as phasors, we're dealing with them as the exponential part that has this complex number in it, and it just makes it a lot easier to work with rather than having sines and cosines. It's just, and whoever was the first person to figure that out, it's brilliant. They don't spend a whole lot of time like in the circuits, like in the AC section, showing what you would have to do if we didn't have this convention, but it would be a mess. Okay, so list the 3 standard forms for complex numbers. For each number below, state what form it's in, and then convert it to the other 2 forms. So, did you have something like this for homework?
I think so.
And I'm wondering if I am what. Okay, so A equals 6. So that is, the real part is 6 and the imaginary part is 0. And so the 3 different ways that we're going to be writing these are going to be rectangular, polar, and phasor. So we'll have A plus JB, and we'll have E, or AE to the J theta, and then we'll have magnitude and angle theta. So the magnitude of a complex number is the square root of a squared plus b squared. And we'll see why that's true for a couple reasons later on. And the angle is, you know what, I want to do a different section first and come back to this. I want to do number 7 first,
Okay.
and then we'll come back to this. Okay, so 3 plus 4j, we're going to graph these in the complex plane. So that means this is the real axis, and this is the imaginary axis. And 3 plus 4j means that you go 3 in the x direction. And how are these? And 4, I have 1i, 2i, 3i, and 4i. Like that. And then this shows why we treat it as a vector. So that is our complex number. And this side is the real part, and this side is the imaginary part, and the magnitude is the square root of a squared plus b squared, which would give us 5. And the angle, we want to give our angle, it's best to give it from, to be in between plus or minus 180 degrees. And so this angle on this one would be the inverse tangent of 4 over 3. And if you do the inverse tangent of 4 over 3 on your calculator, you get 53.13 degrees. So that would be the angle for this one. That's not part of this problem. But we have to be careful when we use our calculator, because the calculator is only going to give us a value in quadrant 1 or 4. And if we're in a different quadrant, we have to be careful about that. So let's go back to the problem that I was on, and to figure out the angle, for this first one, if we think of it where it would be on the complex plane, 6, the real part is 6, it's right here, its angle is clearly 0. So this is 6 plus j0, or 6, because its magnitude, its length is 6, e to the j 0 degrees, or 6 angle 0 degrees. Now let's do negative 3 plus 4j. So negative 3 plus 4j, so that's going to be right here. And we know because we know 3, 4, 5 triangles. Do you know 3, 4, 5 triangles? Okay. A lot of people don't know 3, 4, 5 triangles, but we know 3, 4, 5 triangles. So we know the magnitude is 5. So the one form, the rectangular form, is negative 3 plus j4. And then the polar form will be 5 angle. Now, if we did the inverse tangent of 4 over negative 3, what do we get?
Negative 53.13.
Negative 53.13, which is down in this quadrant, which is why it's important to know that that's not actually the angle we want, because that's not the right angle. And so instead we add 180 to it.
You get 126.86 or 7?
So I say 126.87 degrees. And then, so this is exponential form. I'm sorry, no, that's polar form. This is the phasor. The phasor is called polar form. I call both of these polar form, but this is really polar form, the phasor form. And then the exponential form would be 5 ej to the 126.87 degrees. If you happen to have a TI-84 calculator, I recommend you watch the video that I posted about complex numbers on the TI-84, because it does some weird things with radians and degrees. If you have the calculator, I always recommend the TI-36X Pro. I have another video that I've posted that'll show you all kinds of good stuff with complex numbers. All the stuff you're learning here is going to be a piece of cake. Once you learn how to do it, you won't have to do it anymore. Your calculator will do it for you, but you do have to learn how to do it. Okay, so 10 angle 60. So this tells us that this is the polar form right here. So 10 angle 60 is the polar form. And that means our exponential form would be 10 e to the j 60 degrees. And our rectangular form is going to be 10 times cosine 60 degrees plus j sine 60 degrees, which is 10, and the cosine of 60 is 0.5 plus j, and the sine of 60 is square root of 3 over 2. And so this becomes, the rectangular form is 5 plus j 5 square root of 3. B equals 4j. So that is on the imaginary axis. So it's right here. So its rectangular form is 0 plus j4. Its exponential form is 4e to the j 90 degrees. And its polar form is 4 angle 90 degrees. Now, this next one is in radians, and you can tell because it has pi over 4, and also doesn't have a degree symbol. So degrees are always supposed to have a degree symbol, and radians don't have a degree symbol. So this is saying it is 4e to the j pi over 4. Pi over 4 is 45 degrees. So we know that this one is at, there's my marker. So it's at 45 degrees, and its magnitude is 4. And that angle is 45. So this side is 4 sine 45 degrees, and this side is 4 cosine 45 degrees. And so the exponential form is given 4e to the j pi over 4. Its polar form would be 4 angle pi over 4. No degrees because it's not a degree, it's radians.
Oh, so we don't convert them?
You can, I don't, it's, yeah. You can if you want to. So 45 degrees or pi over 4, it's the same thing. The old textbook almost always used degrees. I don't know because I haven't used the new textbook yet. And then in rectangular form, the cosine and sine of 45 degrees is square root of 2 over 2. So this would be 2 square root of 2 plus j 2 square root of 2. I did remember to start recording again. Either that or I continued recording when I didn't mean to be recording. Let's see. Now I'm about how you're going to be using these in circuits and how we transform things. So what we do when we have AC circuits is we transform things from the time domain to the frequency domain. And so what that means is rather than having the signal is changing, it's a function of time, but we're not going to talk about it as a function of time, we're going to talk about it as a function of frequency. And we'll find that to transform things, the resistances are just not going to change at all. Resistances will just be resistances. But, and we're going to go from what in circuits 1 we had resistances, and now we're going to talk about impedances. And the nice thing about impedances is that all impedances add together like resistors did in circuits 1. So it doesn't matter if it's a capacitor or an inductor, you treat impedances all the same, except now they'll be messy because they'll have complex numbers in them. So if I wanted to get the impedance for an inductor, that's going to be J omega L. So J is our imaginary unit, the square root of -1. Omega is the angular frequency of our circuit, and an angular frequency will be given in radians. If you're given a frequency in hertz, that's an F. So a frequency in hertz is F, and omega is 2 pi F. Now, we often are very lazy and call them both frequencies. So if I say the frequency is 60 pi, I'm probably talking about an angular frequency. Right. And so if I give radians, that's definitely an angular frequency. But if I say the frequency is 60 hertz, then that's going to be a regular frequency, and you multiply by 2 pi to get the angular frequency. And you will be given both F and omega in problems, so you just have to pay attention. Now, the capacitance is the one that is like, it really messes things up. So Z over L, or Z, the impedance for a capacitor is, you can write it in one of two ways. 1 over J omega C, which is identical to minus J over omega C. And let's see why that's the same. So if I have 1 over J omega C, and I multiply that by 1, only instead of 1, I'm going to write it as J over J. So if I multiply by 1, that doesn't change anything. So I get 1 times J is J, and in the denominator I get J squared omega C. But J is defined to be the square root of negative 1, and therefore J squared is negative 1. So this is J over negative omega C, or minus J over omega C. Now, frequencies are always going to be positive. So our impedances, you can tell by your impedance whether you have a resistor, an inductor, or a capacitor. This last one should have been a capacitor. By its imaginary part. A resistor has 0 imaginary part. An inductor has a positive imaginary part, and a capacitor has a negative imaginary part. So let's go back now and look at problem 8. Identify the element types from the impedance. For each impedance at the same angular frequency omega, decide if it corresponds to a pure resistance, pure inductance, or pure capacitance, and if possible, give the component value. So here we're saying Z equals J10 omega at 1,000 radians per second. So is this going to be a resistor, an inductor, or a capacitor? It's got an imaginary part, so it's not a resistor. Resistors are real.
Oh, it's positive, so it's an inductor.
So it's an inductor. And we know that the impedance for an inductor is J omega L. So we know J times the angular frequency is given as 1,000 radians per second, so that's J times 1,000 times L equals J, does that say 10? J10?
10.
So the J's will cancel, as you would expect, because your inductance has to be a real number. So L equals 1 over 100, or 0.01 henries. Or 10 millihenries. Okay, the next one's easy. what do we have here?
Resistor.
Yeah, this is a resistor. And what is its resistance? 47 ohms. Okay, so now this one has got to be a capacitor because it's negative. So we know that and notice that impedances are given in ohms. They're all ohms. So minus J5 equals minus J over omega C, or minus J over omega is 250 C. So I have minus J5 equals minus J over 250 C. So my minuses and my J's can cancel, and I will get 5 times 250C equals 1, or C equals 1 over 1250, or C equals
0.0008.
0.0008 farads, or 0.8 millifarads, or 800 microfarads.
Which one should we use?
I don't think it matters.
Okay.
Okay, so now pause. Okay, so let's say we have a series impedance of a resistor, an inductor, and a capacitor. And we're going to do this in symbolic form, and then we'll use our calculators to get it in, to get the net impedance. So by the way, so one thing, impedance equals resistance plus J reactance. So the resistance comes from the resistor, and the reactance comes from the capacitor or the inductor, and it has the symbol X. So this is X, and this is R, and this is Z. So Z equals R plus JX. Okay, so in series, I'll have a resistor plus a capacitor plus an inductor. And when I change these two impedances, sometimes I leave them drawn the way they are. Sometimes if I'm putting them together, I might just make a little box out of it, and just put the impedance in the box, because now I'm treating them all the same. And so, but they're all in series. So we're going to add them up. We're going to say R plus J omega L minus J over omega C. So now what we want to do to find what the reactance is, this is R plus, and I'll factor out the J, and I'll have omega L minus 1 over omega C. And then if I get a common denominator, I'd have omega squared LC over omega C minus 1 over omega C. This is R plus J omega squared LC minus 1 over omega C. But I don't feel like that's any simpler. I thought it might be, but it's not really. So, and so our resistance is R, and our reactance is omega L minus 1 over omega C.
And that's good enough?
Mm-hmm.
Okay.
Okay, so now I have some numbers, and we have to figure out the total series impedance for different frequencies. Now notice the frequencies are given in hertz, so we need to change these to angular frequency. So omega is 2 pi times 20, or 40 pi, or my calculator's way over there.
Sounds
There's
right.
not a thing I can do about it. I mean, that's, yeah.
All right, 125.66.
6, and that would be, units would be radians per second. And so we know that our total impedance is going to be 10 plus J omega L minus 1 over omega C.
Okay.
10 plus J times 125.66 times L is 0.1 minus 1 over 125.66 times 100 times 10 to the negative 6, because those were microfarads. And I just realized I don't have an excuse because I have a calculator. Oh, that's not the calculator I want to use, but I have the other calculator too.
I mean, I could bring that calculator.
No, that's way too much work. Besides, then it wouldn't show up on the video. Okay, so the nice thing about this calculator, and it is the one on this screen says TI-30XS, but the one that you would buy in the United States is the TI-36X Pro. Let me write that down. TI-36X Pro. And you will see that it does just amazing things for you. So if we wanted to add these things that we just found, so I had, my resistance was 10, right?
Yes.
Okay, so first in your mode, you have a choice. Oh, I'm in the wrong calculator. I need... That's what I need. So in the mode, you need, I typically leave mine in rectangular. You may choose to have yours in polar or angle theta, but you definitely want to have complex. And then we had 10 plus. Now J on the calculator will be given as I, times omega was 20 times 2 pi, or 40 pi, so I'm just going to put it in as 40 pi, times L, the inductance was 0.1. Plus, and I'll use my little fraction here, minus J over omega, which was 40 pi, times the capacitance, which was 100 micro. So I'll do 100 EE negative 6. And it does all of the simplification for you, all the rationalization. So we didn't do any of the problems where we had to rationalize and get the imaginary number out of the denominator. We'll do that next time. But this just does it all for you. So you have 10 minus 67.01 J. Okay, now I'm going to skip down to the 200 hertz now and see what changes when we go to 200 hertz. I'm just going to go to my calculator and I'm going to add a 0 to each of those numbers in there. So on the calculator, when you want to add something, you do second and insert, and that'll make it so it doesn't write over, it just inserts it. So I wanted to add a 0 to that 400 pi, and I want to do second, insert, and add a 0 to that 400 pi. And notice I get 10 plus 117 J, 117.7.
And what was the first answer?
The first answer was 10 minus 67.01 J. This is 10 plus J, 177.7. So as a whole, is our circuit acting more capacitive or inductive at the higher frequency?
Higher frequency inductive, I'm assuming. Is this positive?
Inductive because it's positive.
Is that right?
That is right.
Interesting. This kind of feels like doing Laplace transforms and solving that way.
It is very related. It's the whole transforming to a different world to work your problems out that way. So let me see. Form expressions. So we have a phasor, we have rectangular, we have another rectangular. We could also easily have in here, let's just have e to the j 45 degrees, and 2 right there.
I know in class we're doing like presentations, and he wants everything shown up that way, so I'm assuming that's how he wants all this to be.
Alrighty then. Well, let's do that. Okay, so adding is usually easiest done with rectangular, but multiplying and dividing is usually easier done with polar. So let's start with this and say we have 12 angle negative 20 degrees. And let's change this 3 minus 4j to polar. So 3 minus 4j to polar, well, that's 3 in the real direction, 4 in the imaginary direction, and our magnitude will be 5. And we've done that a few times. I think the angle is in 51.1.
I'm sorry. I'm just doing -53.13.
53.13, and the negative is correct here because if we're going 3 in the real direction, 4 in the imaginary direction, that is the correct angle. Times 1 plus j, so if we think about 1 plus j, that's 1, that's right here, that's going to be 45 degrees, and that's a triangle with sides 1, 1, square root of 2. So this is going to be, whatever the square root of 2 is, 1.41, I think, angle 45 degrees. Plus 2. Now I told you the addition is going to be easier to do in rectangular, so I'm going to go ahead and change this to 2 sine 45 degrees plus j cosine 45 degrees. So the multiplication and division will,
Why did you do this 45
and we instead of 40,
I guess it's the same thing either way, right?
no.
Cosine.
Oh, no, this is wrong. It's backwards. It's cosine and then sine. Cosine 45 degrees plus j sine 45 degrees. And this one should have been 45 degrees, not 40 degrees. That was the 1 plus 1, 1 plus j. And our angle here will be negative 20 minus negative 53.13 plus 45. So we do 12 divided by 5 times square root of 2. And I get 3.394. And then I do negative 20 minus negative 53.13, so plus 53.13 plus 45. This should have been, put all that in parentheses, angle. So this angle minus this angle plus that angle. 78.13. Which is 1.41 plus 1.41 j. So now I have .394 angle 78.3. So I want to change that to rectangular. So 3.394 times cosine 78.3 plus j sine 78.3. And yes, you're right, back when I had these backwards, it still would have been the same, but it was still not right. I get 3.394 times 0.2027 plus
I
J,
think it's 78.13 degrees.
oh, 78.13. Point 20569 plus J .979, and all those times 3.394.
It's a little math, which is still really wrong.
Yeah, well, I'm going to show you how you will be doing these later because I don't really stand much of a chance with this. 0.688. Okay, so that now is what this part is in rectangular, and then we're going to add to that 0.141 plus J 1.41.
Does it matter if you put the J on the front or the
It does
back?
not. Can you tell me what you got?
I got 4.7356 for the J part. Plus, I could be wrong. I got 2.1123 for the real part.
.688 plus 1.41. I just can't. I don't stand a chance with any of this.
So I got point
So,
six.
so tell me what you got.
Okay, I got 0.6981 times. Plus square root 2. I got 2.112.
2.112 for the real part,
Yeah,
and then for the imaginary part.
I got. See, I did. 3.3214
Uh-huh.
plus square root 2. 4.736.
Okay. Now let's take a look at so here's the problem we just did. Okay, so, and I am going to say I've got, that's the wrong calculator. That's the right calculator. Okay, so starting with a fraction, and on top I have 12 angle, and I get to the angle by doing second and complex. Angle negative 20. Let's see, what mode am I in? This calculator is slightly different from the American ones. 12 complex angle, there we go, negative 20 over 3 minus 4j, and then get out of the fraction, and then times, open parentheses, 1 plus j, close parentheses, plus 2 angle 45, and I set this one to be in polar mode, and then to change that to rectangular, I go to second complex, convert to rectangular, 2.11 plus 4.77j. Is that close to what we got?
Yep, closest.
Closest? Yeah.
2.11 to get 4.736.
Yeah. Yeah. So you can mix modes and do all that. You just have to be careful, but it all works.
That's pretty cool.
It is very cool, very handy. And with that, I'm going to stop this.